we're going to finish up talking about bonding, covalent bonding, and orbitals. And now we're going to move into molecular orbitals. So let's pick up where we left off last time. And let's get that out of the way. There we go. Okay. Remember the localized electron model, the valence bond theory, and the localized electron model, which is derived from it, assumes that electrons belong to each atom, and they're not completely given up in a covalent arrangement. They're just shared. But the orbitals that the electrons occupy simply overlap from one atom to the next to form the bond. That has its limitations, and we discussed those last time. We needed a better model, and the molecular orbital model does a fairly good job of solving some of those problems. In fact, once the molecule forms, and during the formation of the molecule, those atomic orbitals are transformed into orbitals that belong now to the entire molecule, not to just individual atoms. What that does is it delocalizes the electron density in the molecule, and anytime you can delocalize electrons, you stabilize them. You lower their energy level, which is a stabilizing force. Somebody else dinging in, Michelle. Gang's all here. Okay. Just a comment about the term orbital. That's sort of a holdover from Niels Bohr's planetary model when we first talked about electrons orbiting the nucleus. So we still call them orbitals, but you have to understand that they're not really orbitals in the planetary sense. They're just sort of grandfathered into our terminology. And that happens a lot in chemistry, unfortunately. Okay, this is a side-by-side comparison of the two. The localized electron model relies on atomic orbitals. Molecular orbital relies on a new class of orbital called the molecular orbital. In the quantum mechanical model of the localized electron model, the solutions, the mathematical solutions that give us the regions of space and the energy levels that these electrons occupy for atoms are transferred, so to speak, to the molecule. Whereas in the molecular orbital model, those equations are different. A different set of equations describe the molecular orbitals. All right, we mentioned that one already. The difference between localized and delocalized electrons. Here's where they're the same. For any defined orbital in the atomic model, the localized electron model, or the molecular orbital model, each orbital can have 2 electrons. That hasn't changed. Level from here, and then it's either here or nothing, or here or nothing. No in-betweens. Yeah, internet connection is unstable again. Okay. So if you've looked at the video I posted, you'll see some breaks in there, a couple of breaks, and that's due to our wonky internet. It probably doesn't like cold weather either. Okay. So how do we create these molecular orbitals? Well, we're not going to go into so much detail that we have to solve equations, right? That's beyond this course and beyond me, to be honest with you. So we'll have a set of rules and procedures that allow us to, for very simple molecules, derive these molecular orbitals from the existing atomic orbitals of atoms that go into the combination. And we're going to keep those, I mean, really simple, like they're only diatomic. Just two atoms, that's it. And we're going to start off with two of the same atoms, like two hydrogens or two oxygens. So we keep the energy levels that are coming from each atom the same level. And then we'll introduce a short discussion of what do you do when the atoms have different energy levels for their same orbital names. The same orbital designations may have different energy levels. And then we'll say a couple of things about that, just to give you a heads up. First rule, the number of molecular orbitals that are created in the formation of a molecule is equal to the number of atomic orbitals that come out of the atoms that contribute to them. So if you have the simplest example, dihydrogen. If you have dihydrogen, right, each one of them has a 1s orbital. Right? So the molecular orbitals for that molecule will be 2, one from each one. So that's conservation of orbitals. We'll call it the law of conservation of orbitals. Now, how does that happen? Well, we need a discussion of the concept of interference. If you've never been introduced to this, interference, this is in the physical sense, not the political or personal or cultural sense. Interference is how waves interact. So I've got a little video. I think it's probably the next one. So we can carry over also descriptions of the bonds between atoms in a molecular orbital. If the electron density of the bond is on axis between two atoms, we still call it a sigma molecular bond. And if it's off axis, we call it a pi molecular bond. So that's a carryover from what we've studied so far. Just to reinforce, if this is not obvious to you by now, once you form the molecular orbitals, the atomic orbitals don't exist anymore. They're gone. You can't have both at the same time. It's either one or the other. So in this model, molecular orbitals are created, atomic orbitals are gone. They are no more. Okay.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. once again, we have constructive interference. So constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
All right. Rather than a guitar, I would have chosen a wind instrument. It makes more sense to me, probably because I don't play the guitar. But the concept of a standing wave is a product of interference of a wave upon itself. So when you confine a wave to a certain space, and we can think of, I think we've mentioned this before, we can think of electrons as waves. Right? Matter has wave properties, and waves have particle properties, just like light. So when we think of electrons as waves, then we are able to, in fact, the quantum mechanical equations are wave equations, and they treat electrons like waves. So when you solve the problem, you're actually looking for regions of space where you have constructive interference. The destructive interference is a place where you have nodes, where there's no probability of finding the electrons. All right, I'll do as usual. When I process the video, I'll insert the original here, so it'll be won't be a copy of a copy. So this is probably going to tell you what I just said. Since we can treat electrons as waves, these terms can also be used for electrons. The superposition is what you saw in the video when the waves approached and overlapped one another. They were superposed. And in the process, we got interference. Sometimes we got constructive interference, right, where the highs reinforced one another and the lows reinforced each other, or where you got a high and a low coming together and you get cancellation. That's destructive interference. You can form very complex patterns when waves interact. If you have a wave of a different wavelength trying to overlap with a wave of a different wavelength, then you can get some very complex patterns. In fact, we use that in communications now. In its simplest form, AM and FM radio has what they call a carrier signal, a wave that is the wavelength that you dial in on your radio. Like, for instance, I listen to 101 FM every day, 101 megahertz. That's frequency, not wavelength. But when you tune your radio to that wavelength, what the radio does is it has electronics built in there that destructively interfere with that particular signal, the 101 megahertz. And it effectively removes that signal from what's coming in, and what's left over is the information. And that's what comes through your radio is talk radio, which is 101, or some other music or whatever the case may be. So that's using constructive and destructive interference in reverse. Okay, so what does this look like when we're talking about electrons? Well, if we have constructive interference, we produce what we call a bonding molecular orbital. And notice between the two atoms, and these are both hydrogen atoms, between the two, the density here, they overlap constructively, we get an increase in density between the atoms. That's your sigma bond. But they can also, these wave patterns can also interact destructively. And when they do that, we get a node in between the atoms. This is called an anti-bonding orbital. So we have bonding and anti-bonding orbitals formed from the two atomic orbitals. Right? And that's simply due to the wave nature and how the waves interact. They interfere with one another. And in this way, we conserve the orbitals. Right? We have two atomic orbitals coming from here. We don't have four, we have two. And if they interfere a certain way, you get anti-bonding. If they interfere another way, you get bonding. So we have two molecular orbitals formed from the two atomic orbitals. The CHEM101 here was the bonding orbital. It is typically at a lower energy level than the atomic orbitals from which it is formed. And the anti-bonding orbital, the MO2 in our diagram, the anti-bonding is higher in energy. So, for the strongest bond, you want most of the electrons in these orbitals and as few as possible in those orbitals if you want a strong bond. And we're gonna look at how to calculate a number that tells us whether the bond is very strong or only slightly strong or weak or non-existent. That'll come in a couple of slides. Okay, now here's one way that we can represent and one way that we can use to combine two atomic orbitals here. This is one atom of hydrogen on this side, one atom of hydrogen on this side, and this is the molecule that forms in between, and its orbital structure, molecular orbital structure in between. That's a simple way to draw it. You just have an energy scale here, and then across here you have your atomic orbitals, and then your molecular orbital. And these are derived from just the 1s orbital. So you're going to get one at lower energy, which is the bonding orbital. And you get one here is the anti-bonding orbital. So the molecular orbitals, the convention, in fact, I think it's on the next slide. How we label them. Yeah. How we label these bonds. Well, since you've only got one here, the only possibility is the sigma. Right? You form the sigmas first, just like in atomic, in our localized electron model, you form the sigma bonds first, and only after that can you form the pi bonds. So these are the only things these are the only orbitals that we can derive from them. So this is going to be a sigma, and this is going to be a sigma. But this one is going to be derived from the 1s on each side. And this one is derived from the 1s, but it is anti-bonding. And we use that little asterisk or star to designate an anti-bonding orbital. So we get a sigma bonding and a sigma anti-bonding. And then we put the electrons in, right? One electron from each here. And remember, when they go in the lowest orbital first. That hasn't changed either. So we put both of these electrons down here because this orbital can hold two. Okay. But this one of them has to change its spin, right? Because we can't have two electrons in the same orbital with the same spin. They have to be opposite spin. So notice in this scenario, when we form a dihydrogen molecule, there are no electrons in the anti-bonding orbital. That's a good thing if you want a strong bond. Okay. Okay, we can use a shorthand also, like when we drew the electron configurations for atoms. We had a shorthand where we could string the orbitals across like that. You can do the same thing for molecules. Only you have to know a little more about the energy level because it's from low energy on the left to high energy toward the right. And then you can fill in electrons. But we haven't got there yet. We need a little bit more complicated molecules to get a feel for how they build. There we go. It's just saying the obvious. Orbitals are conserved. So for F2, let's see, I might need a little more space for that because it's got more valence. Also, and this is the energy I've got right here. Also, very often when we're for convenience, we only put the valence atomic orbitals and make molecular orbitals out of valences. But to be complete, you have to include also the core electrons, because once you put them together, then all the electrons belong to the molecule. But we typically just write the valence electrons into their orbitals. So you might see it might start at 2 or it might start at 3 and leave the rest of them alone. Okay, so for F2, we know we have 18 electrons, and well, that's not a good example. Hold on a second. I'm sort of jumping the gun there. Let's look at fluorine's atomic orbital structure. It has 9 electrons each, right? 1s2, 2s2, 2p7, right? Nope, sorry. 2p5. There we go. Okay. P7. Right, nobody caught me on that one. P's can't have 7 electrons. Okay, so if we leave the 1s out, it would be down here somewhere. But if we just draw in the 2 levels, then we have a 2s here and a 2s here for that fluorine and this fluorine. Okay. And then we have P's. We have 3 P's here, 2P and 2P. Right? So these are fairly well behaved. When you have both atoms are the same element, they're fairly well behaved in the way they combine. So these 2 S's are going to produce a sigma from the 2s, derived from the 2s, and a sigma derived from the 2s star, antibond. And from the 2 P's, we're going to form a 2s, a 2p sigma, and a 2p star sigma. So, and in fact, I should draw these up here a little higher to be more symmetrical, right here. All right, so we're going to get a sigma derived from a 2p. And then we get another sigma star up here derived from the 2p. And then that means we have 4 left over. So we get 2 here pi's formed from the 2p, and we get a pi star formed from the 2p's. So we have 1, 2, 3, 4, 5, 6, 7, 8 atomic orbitals that goes in 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals. So I'll point some things out. One thing I've already said is, since these are fairly symmetrical, because they're the same element, then the 2 s's stay down here, separated from those. Once you get different elements, sometimes these can switch places, so that gets kind of messy. And then we've got just to show. It gets kind of busy in here, but you've got a sigma, and a sigma star is actually higher energy than a pi star. So you get the sigma and the pi, and then you get the pi star and the sigma star. And it should follow that pattern. Yes. Okay, notice that we've got the 1s is put in here, right? I left the 1s out. It would go down here, just like this one. And then the 2s here with sigma, with a sigma star will go there. And then you get to the pi 2p here, and then the pi star here. Notice that there's no sigma star from the 2p in that arrangement, because we've used up all the electrons. They're only 18. So if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Did I say 18? Oh, I don't have the 1s's down here. So those are all the 2 levels, the principal quantum number 2 levels, and there's nothing up here. And notice when I was filling these out, they're at the same energy level. I did up and up before I could go back and put down and down. It's the same thing for molecular orbitals as it was for atomic orbitals. Okay, so that's kind of messy, but this is the shorthand way. And if you know how these orbitals are built energy-wise, from left to right increasing, then you can write shorthand this way and fill things in pretty quick. Okay. All right, so here's how we, when we were in the localized electron model, we described sigma bonds as sharing 2 electrons between 2 atoms. That's a bond. And then if we have any extras and we need double bonds or triple bonds, then we have those 2 formed for a double bond, maybe 2 more like nitrogen, form another one. So we have 3 bonds. Well, in the molecular orbital model, you don't have to have whole numbers. You can have fractions in what we call the bond order. We call it the bond order, so we sort of distinguish it from the bond that we would be discussing in the localized electron model. And the way you calculate it is, you look in here, once you get your energy diagram set up, and you look for first the bonding electrons, right? The ones that don't have a star. So we got 2, 4, 6, 8. We have 8 bonding electrons. And then you subtract the anti-bonding electrons. So we have 2, and 4, and 6. 6 anti-bonding electrons. Subtract those, and then divide by 2. And that's equal to, do that right? Yeah, 8 minus 6 is 2, divided by 2 is 1. So the bond order for this molecule is 1, which roughly corresponds to a single bond. That's one way to think about it, recognizing that bond order doesn't have to be a whole number. So you could come up with maybe a 1.5 bond order, which is neither a single bond nor a double bond, but something in between. And that probably would be good for, remember when we had to use resonance structures because we had a double bond here and a single here, but we know that they're all equal. Like, and I drew that that model of let's see, nitrate. Like that. But we could have 2 other different ones, put the double bond here and the double bond there. And you could, then we'd have to resonate them with a localized electron model. But with this model, we know that the bond orders here are 1.5. So that allows us to write one structure using the molecular orbital model, whereas with the localized electron, we have to do resonance. Okay, so bond order for hydrogen, dihydrogen would be 1. Okay, because we had 2 electrons in the bonding orbital and none in the anti-bonding, so 2 minus 0 divided by 2 is 1. That was fairly simple. Now what happens, I'm not going to redraw it, so we're going to rely on the slide for this one. What happens if we form an ion out of our dihydrogen? Say H2 minus, we add an electron to it. Right? What does that do to the molecule in terms of molecular orbitals and its stability? So that's one thing that the bond order can tell us. Is it more or less stable than the neutral H2 molecule? Well, where are we going to put it? If we got an extra electron, the next place it goes is right here in an anti-bonding orbital. So you probably guessed that that destabilizes it. Right? 2 minus 1 divided by 2 is a half. So the bond order is a half. It's not even a full single bond. It would be less stable than the neutral diatomic molecule. Oh, we've got a video coming up.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the 2 nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second-row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, Right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
Okay. That was a long video, and it hammered on some ideas we've already covered. But it did introduce some animation that maybe helped understanding. So there was a topic mentioned here called on the slide after this one. Right now, we're going to define what we've been looking at this point is homonuclear molecules. That is, those that are made up of the same element. 2 identical atoms. And consequently, actually for most molecular orbital scenarios, the valence orbitals are the dominant players. So we typically don't even deal with the core electrons, even though we recognize that they are part of the molecular orbital system. They still, as molecular orbital, as core molecular orbital electrons, do some shielding and don't interact so much with the bonding. But we have to include them because of the concept of delocalization. All the electrons in the molecule are delocalized over the entire molecule. Okay, so a term was used called paramagnetism. Paramagnetism is a property of a substance that causes it to be attracted into a magnetic field. And it's predominantly due to uncanceled angular momentum. So when you get an electron in there that's spinning one way, and it has another electron in that orbital with it spinning the other way, let's say they go like this or like this, they cancel one another out in terms of their magnetism. But if they're in separate orbitals, if those 2 electrons are in separate orbitals and they have identical spins, then they don't cancel each other out, and they can be influenced by an external magnetic field. That leads to paramagnetism. If, on the other hand, all of the electrons in the molecular orbital system are paired, then they have no magnetic field of their own to speak of, and they are designated diamagnetic. The example there is nitrogen. Right? The dinitrogen molecule has all paired electrons. If you pour nitrogen into a strong magnetic field, it just goes right on through. That's liquid nitrogen. If you pour liquid oxygen into that same field, it will sit there until it can't hold anymore, and then it'll stay there until it evaporates. We can actually measure the strength of this paramagnetism or lack thereof in molecules. We put them in a special device. This is an artist's simplification, but you have a balance that measures the force as you lower this sample into the magnetic field, and you can derive a value of force for the sample that goes into that field. If it feels no force, then it's more than likely diamagnetic. If it feels any force, it's paramagnetic, and then depending on how many unpaired electrons are in its molecular.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and antibonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n = 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 antibonding electrons, including the sigma 1s star antibonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have two unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, I'll let this one run, even though it's kind of long, because Professor Dave introduced the concept of SP mixing. When I showed you the fluorine diagram, we had the star, the sigma star, is higher than the pi star. And that's what you would expect if there's no significant mixing of the 2s and the 2p orbitals. But as you move to the left in a given period, you get energy levels of those orbitals close enough together that they mix, and they flip the bonding orbital order instead of the instead of the sigma being here and the pi being there, now the pi is down here and the sigma is there. No, I'm sorry. That's not right. We would expect, with no mixing, to have the, and this has to do with the, it affects the way the p orbitals interact. So with no mixing, we would have the sigma, the pi star, and the sigma star in that order. But when you move to the left, when you get to the left, then the dividing line seems to be between nitrogen and oxygen. So when you move from oxygen to nitrogen, going from right to left, now we get these flipped. So now we get sigma here and pi here, and the anti-bonding stay the same. So you really only have to be concerned with these two. Nitrogen to the left, these flip, and oxygen to the right, the sigma's on the bottom. And I've included this chart, plus another one actually, in the review document. So because it's in the review document, that means it'll be on the exam also. So you don't have to memorize it. This is another way of looking at it. In this case, we've actually put the electrons in with no sp mixing on this side, oxygen and fluorine, and nitrogen, carbon, and boron on this side, where you have sp mixing. And we put the number of electrons into the valence molecular bonds, for lack of a better term. And we find that when we do that, we can predict their magnetic properties. So diboron is paramagnetic. In other words, it has unpaired electrons. Whereas dicarbon and dinitrogen have all paired electrons. They are diamagnetic. And we've seen oxygen before. And fluorine is also diamagnetic. All of its electrons are paired. And we calculated the bond order down here. And the reason we have this observed bond association energy or bond strength is just to emphasize That's a single bond, that's a double bond, that's a triple bond. There's a double bond. Notice the double bond here, the bond order of 2 for oxygen is actually a weaker double bond than for dicarbon. So it's all relative. All right. Another way to look at it from a practical standpoint, with no SP mixing, the pi and the pi star are in the middle, and the sigma and the sigma star on the outskirts. But if there's mixing, you get the pi by itself and the sigma, and then the pi by itself and the sigma. It's another way of looking at it. Okay, so what about heteronuclear molecules? Those in which we have two opposing, two different elements. Carbon monoxide, in this case, would give us a structure. Notice that we're starting off, oxygen has a lower atomic energy for its 2s and 2p orbitals because it has a higher effective nuclear charge than carbon does. Right? Carbon's only got 6 protons and oxygen has 8 protons. So that lowers the overall energy. So we're starting off here and we're trying to mix them. We're trying to form molecular orbitals from these atomic orbitals. And that's where it gets kind of messy. What we try to do first, as a practical matter, is we try to mix S's of the same principal quantum number and the P's from the same principal quantum number. That's not always possible, but when we can, we do. So in this case, we have this 2s forms a sigma star from an S and a sigma from the S's. And then this one, 2p, forms the sigma p and the sigma star p and the 2 pi stars and the 2 pi's. What's interesting is when we predicted the polarity of a bond, we looked at electronegativity. And in this case, oxygen is more electronegative than carbon. So we would predict that the bond would be polar toward the oxygen. Well, actually, it's things like that. So we would have a polar bond that way. If we look at the molecular orbital model, we see that the energy level derived from the oxygen is lower than the carbon, which means that the electrons would actually prefer to spend their time at lower energy than at higher energy. And when we look at the mixing, we find that there are many more electrons here, bonding electrons, closer to the original energy level of the oxygen than they are to the original of the carbon. So that's another way of explaining the polarity of the bond. The molecular orbitals tend to be, the electrons had to change less to make the molecular orbitals from oxygen than they did from carbon. Okay, so here's another HF, hydrogen fluoride. In this case, we have to mix 2 P's with 1 S's from the hydrogen. So there we have no choice. The molecular orbitals have to mix disparate principal quantum numbers. So we find that the 1s is actually a higher energy than the 2p because the fluorine has 9 protons in its nucleus. Hydrogen's only got 1. So we're going to find that the energy level for this 1s is higher than it is for the 2p of the fluorine. And similar to my previous argument, these electrons that enter the molecular orbital are closer than where they came from on the fluorine side than they do on the hydrogen side. So we would expect the bond to be polar toward fluorine. Okay. And this can be viewed as the driving force for the reaction. When most of the electrons that come from the atoms occupy a lower energy, there's an energy benefit, as one of our videos described it, from the bonding. If there's no energy benefit, the bond won't form. So this is an artist's rendition. We see that most of the electron density is kind of favored toward the fluorine nucleus. And this just states the obvious. Right? The electron pair that's shared is not shared equally. And that gives, and actually the values that are associated with these wave functions can be calculated to predict just that outcome. Can be, not by me. The point we're making here is that whereas the localized electron model and the valence bond theory is unable to predict energies, the molecular orbital model can predict exact energies. Okay, this idea of delocalizing can be expanded into molecules that have resonant structures. In other words, they have two or more equivalent Lewis dot structures that in the valence bond theory, we have to use resonance. But and actually, this discussion combines aspects of both models. So when we see pi bonding, think delocalizing of the electron density, whereas sigma bonding tends to confine the electrons between the nuclei. The pi bonding has electron density outside the axis, and therefore it's more susceptible to delocalizing throughout the molecule. Here's an example, benzene. In an organic molecule, I may have said this before, but I'll say it again. When we draw a structure, an organic structure, wherever two bond lines meet, that's a carbon. In this case, we actually drew the hydrogens, but typically we don't even do that. We just draw the lines, the bond lines. Each one of these is a carbon, and that's one possible structure. And then this is another possible structure. And in the valence bond theory, we have to resonate them. And we don't even draw the hydrogens in here either. Because for carbons, we know that carbons have 4 bonds of some kind. So here we have 1, 2, 3 for that carbon, plus there should be a hydrogen out here. If you don't show it, then we assume it's a hydrogen. Okay, so what does that look like in terms of our localized electron model? Well, we find that we have these sp2 hybridization on each one of these carbons because there are 3 groups. There's a hydrogen, 1, 2, 3, so we have sp2 hybridization. And that leaves an unused p orbital on each one of these. And that's where you get your overlap. Well, it's not like we have an overlap here, and then an overlap here, and then an overlap here, and the others are left out. Because we know that all the bond lengths and bond strengths, bond energies here are equivalent. They're all the same. So we have to think of it in terms of resonance, or we can actually form a pi system where the electron density overlaps on all of these p orbitals that form a ring structure of a pi bond. So, like I said, we're kind of creating a Frankenstein's monster here with a localized electron model and the valence bond model put together. But the idea of delocalizing stabilizes the molecule. In fact, benzene rings are extremely stable. I've gone over, and I think this is the last slide. Well, we're close. So I won't tell you my story. We just go from there to the next slide. The nitrate ion would be the same way. Remember, we have those three equivalent structures that resonate, but we know that all the bonds are equal. So this pi bonding system delocalizes electron density over the entire molecule, and that stabilizes the molecule. Now, this is a method of analysis, the photoelectron spectroscopy, that confirms the energy levels for each of the molecular orbitals for a given molecule. We shoot high energy photons at the molecule and note the energies of the ejected electrons. If you've had physics before, you know that the energy of, let's see. So I'll just use the energy of the photon is equal to some work function. Let's say, how much energy does it take to get that electron off, just get it off of that molecule. And then whatever's left over is kinetic energy. Okay, so we know the energy of the photon we're firing at it. We can measure the kinetic energy of the electrons as they exit. And the difference is that work function. That tells us the energy of where the electron came from. And we use that information to confirm that the calculated energies and the experimental values for these, using the molecular orbitals theory, confirms that we can calculate those energies and confirm them experimentally. So this is something that the valence bond theory could not do. Okay, I guess that's it. Yep. So have a good Thanksgiving. We'll see you back Tuesday week from Tuesday.